So let me welcome you to this class on reinforcement learning. I've given this class twice so far at ASU in 2019 and 2020. There's a lot of material on the internet about the class, including video lectures and slides. Each year is a little different. Well, last year was very different because COVID happened, and it disrupted a lot our class. But I try each time to bring up-to-date material, bring up to the forefront of research, and so if you've taken this class before, there will be something for you this time as well. What I'd like to do today is give you an overview of what we are trying to accomplish, an overview of the subject, and get a little bit into our material. Here's my outline. Here's my outline. I'm going to start with AlphaZero and AlphaGo, some very impressive successes of reinforcement learning that happened recently and sort of propelled the field to the forefront in the front pages of the newspapers. And I'd like to mention to you how AlphaZero and the techniques used in its development are also relevant into our course. I'll make the argument that our course generalizes the ideas in AlphaZero to a far broader domain, including engineering, operations research, finance and economics, and so on. So I'm going to start with a few slides on AlphaZero, and then make some historical remarks and bring out some of the general concepts, say a few things about what we're trying to accomplish in this class, and also give references and so on, and talk about dynamic programming, start talking about dynamic programming. Dynamic programming and reinforcement learning are very closely connected, as I'm going to argue in this class. Approximate dynamic programming can almost be used as a synonym to reinforcement learning. And I've been using this term, approximate dynamic programming, and also neurodynamic programming as synonyms to reinforcement learning. But reinforcement learning is the most popular, is the more popular name, so I'm using reinforcement learning in my title and presentations. So we're going to talk, however, about exact dynamic programming, and deterministic problems in particular, and how they relate to approximate dynamic programming and reinforcement learning. Then I'm going to give some examples. A subject that's not covered in the mainstream reinforcement learning literature is discrete optimization and very difficult intractable combinatorial problems or combinatorial optimization problems. We're going to see how they can be handled by dynamic programming, therefore opening the door to using reinforcement learning techniques for their solution. And then I'm going to say a few things about how the course is organized. So let's go to AlphaZero. AlphaZero is a program that plays chess and also other games. The predecessor of AlphaZero was AlphaGo. AlphaZero plays better and also uses somewhat different algorithms. AlphaZero is very remarkable. It plays much better than all humans and also much better than all chess programs. And Another thing that's very remarkable is that it plays differently, amazingly differently. It has discovered new ways to play a very old game like chess or Go. And it has another thing that's impressive is that it has learned from scratch, just given the rules of the game, by playing against itself without human instruction, and was able to beat other computer programs, the top computer programs, within 4 hours. So for 4 hours, it played against itself, it learned the game and learned it better than other computer programs. And moreover, its algorithms are portable in the sense that the same are used for other games like Go and shogi, Japanese version of chess. So all of this is just extremely impressive. The methodology, however, that AlphaZero uses is not so new. The ideas were still around 25 years ago, except for some wrinkles, some very clever implementation. And the methods are really the principal ideas of this course. What we're going to cover in this course is the generalized versions of ideas that underlie AlphaZero. And these are offline training using neural networks and the fundamental method of dynamic programming called policy iteration. The neural networks are used to approximate what's called a value function and a policy of AlphaZero. There's a lot of parallel computation that has been used in its development, its training. These 4 hours of training that you see here would have been perhaps months and years if it were not for the tremendous computational power that has been brought onto the training process. Finally, once the program was trained, it also has another algorithm that plays online, like plays against you or me or other computer programs. And this involves multi-step look ahead, cost function approximations. And I think that people sometimes do not quite realize that there are two algorithms involved in AlphaZero. One that involves offline training before it starts playing against any opponents, and online play, which is used while used by any player that has access to it. Okay, so let me get into the offline training process of AlphaZero and give you an idea of how it works. And incidentally, feel free to ask questions, to interrupt me. To do that, you have to unmute your microphone and then just shout. Don't type anything in chat because it may take me some time to see it. Okay, so the offline training of AlphaZero involves the construction of a sequence of players. A player is a software that that generates moves in response for a given position. Given a position, a chess position, a player looks at all possible moves that that can be played at that position and assigns probabilities to them. The play probabilities with moves that are attractive, having higher probability. So a play is like a randomized policy. Given the state of the game, the current position, it gives the probabilities by which various moves will be played. So now the player, the performance of the player is evaluated by using data. So we have a player who play a lot of games, we evaluate this policy, and we use what's called a value network. A neural net, this evaluated through using a neural network. So the value network, given a certain position, it provides an evaluation of that position. Then, given an evaluation, an evaluator of the player, the value network, we can generate a lot of games and try to improve using a process called policy improvement and get a better player, a player whose move probabilities are a little better. They are sort of moved towards more successful outcomes of the game. And this improved player is encoded in a policy network, a different network. So the current player plays games that are used to train with data and neural network training an improved player. And these networks are actually deep neural networks, and there's a lot of interesting methodology that goes into the training that we are going to cover sometime later in the course, probably in the second half of the course. The training involves regression. It involves the data that's self-generated by the program itself through self-play. The policy improvement is intricate, and I'm not going to try to give you all the details here. The simpler versions of policy improvement, but the Monte Carlo tree search that has been used by AlphaZero has been particularly successful. Let me also know that there were earlier works. In particular, there was that were very similar, and they go back more than 25 years ago. There was a program called TD Gammon that plays backgammon. Backgammon is a complicated game of strategy and also chance. It's not as difficult as chess, but still a very, it involves a lot of subtleties and intricacies. And Tesoro also had this self-learning policy iteration idea. And later, okay, TD Gammon came out in 1992, and later there was an improvement of TD Gammon that has beaten all, plays at a better level than all humans. So the success of AlphaZero involves ideas from policy iteration and dynamic programming, and also ideas that had been used before in the context of backgammon. Okay, so this is the offline training, and at the end of offline training, we get a player, presumably the best player that has been generated. However, that player, if you play against it, you can probably beat it. Okay, if you're a strong chess player, it's not impressive. That player becomes impressive when it is embedded in an online playing algorithm, which involves what's called approximation in value space, multi-step look ahead, and some other ideas that are going to be central in our class. Okay, so let's see how that works. Let's think of a game as a sequence of positions. Let's say the starting position, we'll call it X0, and the current position, let's call it XK, okay? So that's our current position, and we have this value network and the policy network, which we obtained by offline training. Then we generate a look-ahead tree, a tree of possible moves and counter moves that may go up to a certain depth. We look at the end positions at the leaves of that tree, and then we go forward and we simulate the policy network, the policy, which we call base policy or default policy, for some more moves. And then at the end, the game may not have ended. So we take the position evaluation and we use it as the outcome of this result. So we have several moves that are generated. they are projected forward up to the point where it's a position evaluation, and then we choose the move that looks more promising based on these results. Now, the online player plays much better than the base player. That's important to understand. And in fact, it is due to the online play that we rise from a level that's sort of a strong grandmaster level to a phenomenal level of play. And Tesoro used a similar methodology involving this rollout. In fact, he was the one who suggested this rollout idea, playing for several moves with the policy network that was obtained by training. And AlphaZero actually does not use this middle piece. And I think the reason, at least in its published version, I think that they probably have tried. I'm sure they have tried it. However, AlphaZero has a very long look ahead. So extra look ahead with the base policy does not seem to add all that much. AlphaGo, however, did use this truncated rollout scheme. Okay, so now our objective in this course is to take these ideas of offline training and online play and view them through a more general lens for problems involving dynamic programming with approximations, of course, including operations research, planning type problems, problems from the classical methodology of control, optimal control, including a methodology called model predictive control that's dominant these days in control theory research, and also in robotics where model predictive control is also used. Then we're going to look at multi-agent versions of dynamic programming and optimal control problems, where the decisions are made collectively, are broken down into individual decisions of a number of decision centers, which we call agents. And these agents may communicate with each other, may coordinate with each other, perhaps imperfectly, and they pose special challenges because the search space is very, very big. And we're going to deal with those, however, and we'll extend our techniques to these. We're going to look at deterministic discrete optimization problems, combinatorial problems, like traveling salesman problems, scheduling problems, so routing problems, very difficult problems, and we're going to embed them within dynamic programming and then use approximation techniques to try to solve them, particularly the technique of rollout that I mentioned in the previous slide. Then there's a whole other class of problems that takes difficulty into another level. AlphaZero is, of course, deals with a very challenging game, chess. However, from a dynamic programming point of view, from a control point of view, chess may not be so difficult. This may surprise you, but the main thing that AlphaZero has going for it in the context of chess is that the rules of the game do not change. They're stable and they do not change. You play today, it has the same rules as tomorrow, okay? So it's a stable environment. Now, many control problems deal with a changing environment. They all come under the name of adaptive control. So for example, you may have a robot that may operate in one room and then they may move into another room. And then it will face a different environment. Or it may take a small weight and put it from one place to another, but then it may try to take a much heavier weight and put it from one place to another. That's a different problem. It's a changing environment. So if you want to get a feel for a difficult problem, think of chess, where as you play, after let's say 15 moves, someone comes and tells you, well, your pawns cannot move forward, instead they can move backwards. Or your bishop can move on horizontals. Or I'm going to take away your queen, and you're going to play without a queen and do this, and maybe in the future I'll give you another queen, okay? That's the kind of big changes that in practice we have to deal with in control and decision problems. And we're going to talk about how you deal with those, at least to some extent. It's a big methodology, we're going to touch upon it. But what I'm trying to do here is give you the range of problems that we are going to be addressing. Okay, so now we're going to discuss offline training methods, like in the AlphaZero case of approximate policy iteration, and also another method called Q-learning, and also discuss how we construct these value networks and policy networks. We are also going to discuss online control methods based on what we'll call approximation in value space. This rollout combined with multi-step look ahead and combined with a value approximation. Our subject is going to be motivated by theory. It's going to be based on theory. There's an awful lot of crazy ideas in this field. I think it's very important to be connected with solid methodology. However, there's a lot more there's a lot in this subject that relies on intuition. And we're going to try to, because the mathematics can be very daunting and also not very revealing, we're going to try to stress intuition. We're still going to rely, however, on some mathematical analysis, not very difficult. Moreover, we're trying to find unifying themes within the subject and develop the methodology in a way that allows us simultaneously to deal with different types of problems, like deterministic problems and stochastic problems, with discrete problems that involve discrete decisions from a discrete space, and also decisions from a continuous space. So we're going to rely on theory, try to introduce some unification, but also try to develop intuition. So now let me get into a little bit on the historical background. Are there any questions, by the way? Okay. Now, the present state of the art owes much of its status at a very fruitful union of ideas, complementary ideas from artificial intelligence and reinforcement learning on one side, and decision and control and dynamic programming on the other side. Now, dynamic programming is a very old methodology. It goes back 50 years, perhaps even more. And you hear the name of Bellman, also Shannon, the father of information theory, and also the father of computer chess, by the way. And it dates to the 1950s. Reinforcement learning was sort of a languishing field in artificial intelligence for a long time, but then it got revived in the late 80s and early 90s when people realized that a lot of things that they were doing were connected with dynamic programming, and they could use dynamic programming as guidance, as a guiding light in further investigation. Now, the reinforcement learning side has some very important ideas to contribute in this union. The idea of simulation was very important. The idea of using methods that did not have an explicit mathematical model. Representations using features and neural networks, various heuristic ideas. And these were combined by the ideas of the mathematical ideas of decision control, the principle of optimality. We're going to mention this a little later. Markov decision problems, policy iteration, value iteration, and so on. And now all of this would probably go dormant for a while, except that there was this major success on backgammon by Tesoro in the early 90s. And Tesoro's work was just as impressive, perhaps even more impressive, than what AlphaZero has been in recent years. Tesoro's work was the AlphaZero of the time. And the people became very enthusiastic. I personally got into this field because I was so impressed by Tesoro's work. And Tesoro's work provided the motivation and some confidence on the part of people to see that very difficult problems could be addressed with these methods that were kind of nebulous at that time. There was sort of a hazy understanding about them. Now, following Tesoro's work, there was further algorithmic progress, some analysis, more applications, and the first books came in the mid-90s. Then in the 2000s, there were some mega trends in technology. Machine learning became very important, using data, big data, lots of data. Robotics also became the focus of a lot of attention in the 2000s. There were major successes with deep neural networks. So the whole field mushroomed, starting in let's say in the last 10 years. And finally, there was a great enthusiasm about AlphaGo and AlphaZero, which continues until today. Reinforcement learning right now is the hottest of the hot field of artificial intelligence. It's really hot, and there are a number of reasons for it. Here are the reasons. There is confidence in the methodology, and the methodology is also ambitious and universal. By this, I mean that it applies to a very broad range of optimization problems, from deterministic problems to stochastic problems, from combinatorial optimization problems with discrete spaces to optimal control that has infinite state and control spaces, from one decision maker to two-player games. However, exact dynamic programming is plagued by two curses. One is the curse of dimensionality, which relates to the exponential explosion of the computational requirements as the size of the problem increases. This name, curse of dimensionality, is due to Bellman and goes way back, more than 50 years ago. It was recognized as the principal impediment in using exact dynamic programming. There's a second curse, however. In its exact form, and it is original version, dynamic programming required a mathematical model. Equations, closed form expressions for cost functions, and so on. Probabilistic description of various uncertain quantities. And all of this was very difficult to develop. Now, approximate dynamic programming and reinforcement learning overcomes these difficulties in two ways: by using approximation to reduce the dimension, the effective dimension of the problem, by using neural networks and other approximation architectures, and it addresses the need for a mathematical problem through simulation. In other words, it is not necessary in reinforcement learning to have a mathematical model involving closed form expressions, equations, and so on. It is sufficient to use a computer model. Of course, a computer model implements a mathematical model, but it can implement very complicated models that they would be very difficult to write down. A computer model may contain so many equations that you wouldn't be able to, you would need something like a phone book to describe it, to describe mathematically. So being able to use a computer model in simulation was a major new idea that was contributed by artificial intelligence and reinforcement learning to this overall landscape. Okay, so where are we now? We have a very broadly applicable methodology. As I mentioned, exact dynamic programming applies to a very, very broad range of problems. So we can deal with deterministic problems, stochastic, dynamic, discrete, continuous, games, and so on. We can deal with them because we've been able to overcome some of the difficulties of exact dynamic programming. However, there are no methods that are guaranteed to work in reinforcement learning. The problems are very difficult. The methods themselves involve approximations. To some extent, they are opaque. Neural networks in particular are opaque. You can't figure out what's going on in a neural network very easily. So there's this difficulty that there are these methods that you see advertised in research papers or books, and you try them on your problem, but they just don't work, okay? And they may not work for a number of reasons. Because they're so complicated, you may have made a mistake, there may need some tweaking, the problem may be very difficult, or the method itself may not be suitable for your particular problem. On the other hand, there are enough methods, there are lots of methods that you can try on your problem. Some will not work, but there's a reasonable chance that some will work for any given type of optimization problem. And it's up to you to use your intuition, your understanding of the problem, your understanding of the methodology to be able to figure out how to match methods to problems. And the role of theory here is to delineate the sound ideas from the crazy ideas that you will see advertised. And also there's an art here, and the theory is used to guide the art. Okay, let me also put up a quotation from the neurodynamic programming book that I wrote 25 years ago with John Cisiklis. Okay, this quotation is long. However, you can read it at your leisure, but it sort of characterized the field at that time, and it also still characterizes the field now. It talks about methods, reinforcement learning methods, that aim to provide suboptimal solutions to complex problems of planning, sequential decision making under uncertainty that for a long time were thought to be intractable. That's what really attracted us to the field. There were all these methods that were challenging the state of the art by addressing problems that were completely beyond our capabilities of the day. Our first impression was that new methods were ambitious, overly optimistic, and lacked firm foundation. On the other hand, there were claims of impressive success and so on, which encouraged us. After we wrote the book and we understood the field a little better, we believed that our initial impressions were largely correct. This is an ambitious, often ad hoc methodology, but for reasons that we understand much better, it does have the potential of success with important and challenging problems. In other words, what we said was that this is a hit or miss methodology, but if you try hard enough and you're clever enough, you may be able to solve some very important and very challenging problems. And now this assessment is true today. Nothing has changed from that time from the point of view of from this assessment of the methodology. It's a flaky methodology. It requires a lot of skill and a lot of intuition and a lot of luck to work. On the other hand, you may be able to solve some very, very difficult problems that it was impossible to solve before, including the game of chess. Okay, so now let me go to say a few things about the course. Our course is research-oriented. We want to explore the state of the art at a graduate level. Some special research topics are going to receive more attention, like rollout, policy iteration, and the ideas of offline training. We're going to talk quite a bit about them. and others also, including combinatorial optimization. And the main idea is to provide you with an opportunity to connect this field with your research interests and to explore research in the area. Okay, references. There's a book that I wrote in the first during the first offering of the class at ASU in 2019, and then last year another one that focuses more on the topics that we're going to cover this in this semester. I have put on the internet on Canvas an expanded version of chapter 1 of these two books, which is double in size, and also is designed so that you can get started. You can get some of the basic ideas and get an overall picture of the field and get started. So this is online right now, and we're going to use it as the starting point for. We're going to use for the first 3 lectures of the course. The first three lectures are going to be based on these class notes. Then there's a tremendous amount of material from the ASU course and subsequent work. If you check my website, and I've given in my recent announcement, I've given the website address. It has video lectures, all the video lectures from the 2019 offering, slides, and also research papers that are connected, and has links to a number of things that you can explore. There's a lot of material. The textbooks are basically these two. On the other hand, I don't want to stick you with having to buy these textbooks. So these class notes and this material at my website should be perfectly adequate for you, for most of you. So if someone needs to explore some more, you're free to look at these books. Okay, supplementary references. I have a 2-volume dynamic programming book. It's everything you'll never need to know about dynamic programming. The 2 volumes are more than 1,300 pages. And there's a lot of material, a big portion of those relates to approximate dynamic programming. It's directly relevant to our class, but it goes into dynamic programming and optimal control more in depth. Then there are 2 books that were published in the mid-90s. One was in 1996, my book with John Tsiklis, which is more mathematically oriented than the level that we're aiming at in this class. And there's also the book by Sutton and Barter, who come from the artificial intelligence side. These 2 books give 2 different points of view of the same subject. The emphasis is different, the culture is different, the mathematics are different, but you may consult them and see for yourself. All of these are very relevant to our class. Okay. Reinforcement learning and dynamic programming control have very combined fortuitously to create the present state of the art. On the other hand, these 2 are different communities that have a different culture, use different models, different notation, different language, and I come from decision and control. And I'll use the notation in the language in the mathematical style that's used in that community. On the other hand, if you look at the reinforcement learning papers in the literature, you'll see that they use different terms. And so let me give here some translation, provide you some kind of translation glossary. There's a more extensive one in your class notes. One difference is that the reinforcement learning uses maximization, maximizing value, whereas dynamic programming uses minimization of cost. In reinforcement learning, people talk about the reward of a stage, which in decision control terms is the opposite, the negative of the cost per stage. State value is the opposite of state cost. Value function in reinforcement learning translates to cost function in decision control. All of this is minor, you can easily get accustomed to, but there are some more radical differences in methodology, in terminology. A decision maker or controller in decision control is called an agent in reinforcement learning. Moreover, a decision or control, the decision variables that we use in dynamic programming are called, and control, they're called actions. So in dynamic programming, we select decisions. In control theory, we select controls. But in reinforcement learning, we select actions. Decision and control is couched in the language of dynamic systems, differential equations, difference equations that involve whose state is influenced by control. So this is called the dynamic system or the system. In reinforcement learning, this is called the environment. Okay, it took me quite a long time to get used to this difference, but you'll find environment almost universally in reinforcement learning papers, and you should be aware that it relates to a dynamic system. Okay. Here are some examples of different terminology that we use for various methods. The term learning is used in reinforcement learning. It's part of the name, reinforcement learning. It's also used with many different meanings. Usually, it refers to solving a dynamic programming related problem using simulation. So learning is related to both getting data about the problem and solving the problem. Self-learning, as opposed to supervised learning, in reinforcement learning relates to using self-play, like in AlphaZero and in backgammon. The programs learn by generating data themselves. Now, in dynamic programming, this translates to using policy iteration, okay? People talk about methods like policy iteration rather than self-learning. In reinforcement learning, there's a planning versus learning distinction, which in dynamic programming is translated to solving a dynamic programming with a mathematical model. This is called planning, versus model-free simulation, which is called learning. Okay, notice the multiple use of the term learning here. And to me, that's a little confusing, but that's the way it goes in reinforcement learning. Like I said, there's a long list of other translations that you can find in your class notes. About notation, not only do these fields use different terminology, but they also use different notations. In reinforcement learning, transition probability notation is used. In other words, the environment is stochastic, and the environment goes from one state into another state, and the states are denoted by S in reinforcement learning typically. And this thing here, P of S, A, S prime, is the probability of being at state S. When being at state S, go to state S prime when you apply action A. Actions are denoted by A in reinforcement learning. In control, they are denoted by U. And actions and states are denoted by X in decision control as opposed to S. Now, this notation is standard in finite state Markovian decision problems, problems where there's only a finite number of states. So you can write these transition probabilities in some explicit way. On the other hand, in control theory, we use discrete time system notation, where xk, the state at time k, uk is the control at time k, and wk encodes the uncertainty with given probability distribution, assuming that there is uncertainty because the problem may be deterministic. And this is standard in continuous spaces because when it comes to continuous spaces, this notation is just bad, okay? It leads to very difficult mathematics. It's very uncomfortable to use this kind of probabilistic notation in continuous spaces problems. Operations research uses both types of notation, except that for transition probabilities, they use I, J, and U. I is the current state, J is the new state, and U is the control. Okay. Now, the important thing to remember is that these notational systems are mathematically equivalent. Anything that you can write in one notation, you can write in the other notation also. On the other hand, transition probabilities are very cumbersome for deterministic problems and also for continuous spaces problems. And here's the reason. In deterministic problems, there are no probabilities, okay? The transition from one state to the next under a given control is deterministic. There are no probabilities involved. So to start with probabilities confuses the situation very much. On the other hand, system equations, this type of notation, is cumbersome for finite state Markovian decision problems. So what are we going to do here? For the first 3 quarters of the class, we're going to use system equations. And when we need the transition probabilities in the last quarter of the class, we're going to use them. We're going to use this Pij of U notation because there we're going to focus substantially on Markovian decision problems. And this type of notation is more convenient and more functional, mathematically speaking, than the system equation notation. Okay. Are there any questions so far? Okay, so there is a key idea here of approximation in value space in the context of sequential decision making. This idea is very central, and we're going to be coming back to it again and again. Our basic framework involves a system or an environment that moves from one state into another over time. So at the current time, say time k, we are in a certain state, we apply a certain decision or action, and then we move to a next state, and that marks the current stage. And then we go to the next stage, to the next state, and so on. So we generate a sequence of states through a sequence of actions or decisions, and each one of these transitions involves a cost. We accumulate costs over time, and you're trying to improve our decision-making policy so as to keep the cost low. Now, dynamic programming encodes this framework here and provides the algorithm for solving the problem optimally, making optimal decisions. At the current state, we have many decisions in our disposal, and we apply the decision that minimizes the current stage cost plus the cost of the future stages, starting from the next state where we land. Okay, so the optimal decision is to minimize in this expression overall possible decisions, and J star here is a function, okay? It's a number, the optimal cost starting from some state. Now, this defines an optimal policy. If we knew this J star, then we could minimize this expression and provide an optimal control to apply in every state and every stage. Now, approximate dynamic programming replaces this J star, which may be a very, very hard object to compute, with some approximating function called J tilde. So J tilde is a function of state, and in approximate dynamic programming, at the current state, we look at all possible decisions and minimize, perhaps with some approximations, the current stage cost and the future cost as approximated by this J tilde. And of course, this is not optimal, this is suboptimal. But this is what we do because J star is very, very difficult to compute. So now, how do we compute this J tilde? We may compute the number of ways, and J tilde corresponds to this value network in the context of AlphaZero. For a given state, a given chess position, it gives you an evaluation, gives you a number. But it may be computed in many different ways within reinforcement learning. One possibility is by problem approximation. Okay, J star is the optimal cost of a given problem. Suppose I approximate my problem and use as J tilde the optimal cost function of this related problem, which we can compute by exact TP. Of course, this requires this possibility to be able to compute by exact TP. This is called problem approximation. I can't find J star for the given problem. I solve a related problem, and I use J tilde as J tilde the J star of that problem. Now, another possibility that's used in rollout and also in model predictive control. We use as J tilde the cost approximation to be the cost function of some policy, some suboptimal policy, some heuristic policy. That and the values of J tilde are computed somehow, perhaps according to some simplified optimization process, perhaps by simulation. There are a number of different ways in different problem contexts that you can compute J tilde by a rollout. We can use offline training and data and neural networks or some other feature-based architectures. This is what's used in the offline training of AlphaZero. We compute, and the neural networks serve as function approximators. In this course, neural networks are going to be important. They're going to play an important role. But that role is always going to be function approximation. In other words, we have a certain mapping about which you can collect some data, and we fit the neural network through some kind of offline training algorithm, regression, whatever, to obtain an approximation of this target function that we're interested in. So we have a target function J star, and we can use a neural network to calculate a J tilde, provided we can obtain suitable data, perhaps in the context of policy iteration and so on. Okay, another idea is to use simulation to collect the data to train the various architectures. And various optimization algorithms can be used, gradient descent methods, regression, least squares, whatever. There's a large number of those, and we're going to cover at some point the principal methods. Then there is the dynamic programming idea of policy iteration and self-learning, where we generate sequentially multiple policies. And each is used to provide the data to train the next. So there's a very broad range of approaches to compute approximations, and I've listed here some. We're going to go through all of those over time, and we're going to see how they fit into the overall picture. Okay, So now I'm going to describe exact dynamic programming and motivate it, at least intuitively, for deterministic problems. In reinforcement learning books, in artificial intelligence-oriented reinforcement learning books, deterministic problems do not receive too much attention. That's why they start with this transition probabilities, go straight into Markovian decision problems. On the other hand, I think it's important to look at deterministic problems, both because they arise very often in practice, but also because their methodology is a little different than stochastic problems. They can take advantage of this determinism. So what's a deterministic problem? And we're going to talk first about finite horizon problems. Horizon means the length of time that over which you exercise control. So n denotes the end of the horizon. And here these problems involve starting at a given state, x0, going to state x1 at time 1. At the typical stage, k, we are at a state xk, and then we apply a control uk out of a given set, and a cost that depends on the state and the control is incurred, and there's a transition to a new state, which is deterministic. In other words, according to this equation, an equation like this. In other words, if I give you the state and I give you the control, it is certain that you're going to get this next state given by this function of state and control. There is no uncertainty about the outcome of the transition. By contrast to stochastic problems, where we'll introduce uncertainty. So that's what we mean by a problem being deterministic. Once you apply control uk at a given state xk, the cost of the transition is determined, and the next state is also determined. The control is chosen by this constraint set here, which may depend on the stage and also on the current state. Now, suppose you do this, you apply all n controls, control Q0, U1, and so on. Then there's a corresponding sequence of states that's been generated, and the cost is accumulated over the n periods. There is one cost for each one of these stages corresponding to the controls, and there's also a terminal cost of going from xn minus 1 to xn. Oftentimes it's convenient to have such a cost as well. Sometimes these costs are zero and only the terminal cost matters. So our cost function is this. It's the most general, it's general in the sense that there's a stage-wise cost and a terminal cost. And now the cost is a function of the initial state and the controls that you apply. The intermediate states are determined by this equation. So the cost is a function of this sequence of controls, and the optimal cost is obtained by minimizing over all those controls. And this is what we call the optimal cost function. It is a function of the initial state. It's not just a single number. It's a number for every possible initial state. So if the number of initial states is finite, this is a vector, a finite set of numbers. If the state space is infinite, like continuous, like the real line or n-dimensional Euclidean space, this is a function of a continuous variable, okay? And that's how it is defined. Okay, so now dynamic programming involves a very simple idea called the principle of optimality. Are you guys following? Are there any questions? I see just the names of the boxes, and I can't see your expression, except for only a few persons. But like I said, you may interrupt me at any time and unmute your microphone and shout out your question. Okay, so the principle of optimality. we have a sequence of state changes from time 0 to state n. And at the k stage, after k actions, k decisions, suppose that we have reached a state, and suppose that we have an optimal sequence of actions, okay? So the state of x's, the state trajectory is also optimal. So suppose now that I look at one of these intermediate optimal states, and I look at the tail subproblem running from k to n. So this is the original problem from 0 to n. The tail subproblem is the intermediate problem starting from an optimal state. And I look at this problem, forget at what happened in the past, forget how we got to xk, and try to solve this problem, the tail subproblem. What's the optimal solution to this problem? Well, it doesn't take too much thinking to see that the tail portion of this optimal control sequence is also the optimal sequence for the tail subproblem. Okay? That's the principle of optimality, a very obvious idea. The tail of an optimal sequence is optimal for this tail subproblem. Why is that so? Well, if this were not optimal for the tail subproblem and there was another one that was better, then I could concatenate the sequence that got me to here with this other optimal sequence and reduce the cost of the original optimal sequence, the entire sequence. Put in another way, suppose that you gear up to start from Phoenix to go to Boston, okay? And you calculate your optimal route. And your optimal route goes through St. Louis. And then suppose that you look at the problem of driving from St. Louis to Boston and choosing your optimal route. What will be the optimal route? Well, it will be the tail portion of the route that you have planned for going from St. Louis, from Phoenix onto St. Louis and onto Boston. So this is a mathematical expression of the principle of optimality. If you have an optimal control sequence of corresponding sequence x star 1 to xn, consider the tail subproblem that starts at xk and minimizes over the tail sequence the cost to go. We're going to be using a lot this term, cost to go. From xk star going forward, then the tail optimal control sequence is also optimal for the tail subproblem. So now this principle of optimality provides the seed for an algorithm, the dynamic programming algorithm. It says that I can build an optimal control sequence by using solutions of tail subproblems that are shorter, okay? 1 step, 2 step, 3 step, and so on. So here's the idea. Solve all the tail subproblems of a given time length using the solution of all the tail subproblems of shorter time length. So we can start solving a tail subproblem for the very last stage. So this is a tail subproblem of length 1. Then try to solve a tail subproblem of length 2, leveraging the solution of the subproblem that we have already solved. Then go to stage 3, 4, and so on, all the way to the beginning. According to the principle of optimality, to solve the tail subproblem that starts at xk, I can consider every possible control, solve the tail subproblem that starts at the next state, and that gives me the overall cost of choosing control UK. It's the cost of the first stage plus the optimal cost of the tail subproblem that starts from the next stage. And then all I have to do is optimize overall possible current controls. So here's the dynamic programming algorithm. What it does, it produces the optimal cost of all the tail subproblems, starting from any state and any stage. And it does so backwards. Starting at the end, it goes one step back and then one step back and so on, producing the optimal cost functions of these tail subproblems that are becoming increasingly longer. So we start with the terminal cost, okay? So that's the trivial, the default, the trivial tail subproblem at the end, where we have landed at the terminal state. And then using the optimal cost of the xk plus 1 subproblems, we are at state xk. We consider the tail subproblem that starts at xk. We consider all possible controls uk, and we consider the actions, consider the cost of the first stage plus the optimal cost of the tail subproblem that starts at the next state, and we optimize over all controls. And that's the algorithm. It builds the function j star n minus 1, starting from j n star, then the function j n minus 2, j n minus 3, and so on. At the last step, j stars of x0 is the optimal cost to go from the initial state. So after n steps of this algorithm going backwards, we obtain the optimal cost function. It's j star. And now we are ready to generate the optimal control sequence by going forward. After we have gone backwards, calculate the cost of the tail subproblems and calculating all this j star k, we can generate the optimal control sequence going forward. Starting from the initial state x0, we have j1 star calculated, so we compute this first control. And we compute the next state, the state at time 1 that is optimal. And then we repeat, we obtain u1 star, u2 star, and so on, going forward with this equation. So if I have all these j stars, then I'm in good shape. I can calculate the optimal cost going forward. It's like having obtained the value network and then using online play in AlphaZero. You may view the calculation of J star as the training process, offline training, and then online control generation through this process here. But the fly in the ointment here is that these J stars are extremely hard to calculate. It's just too much calculation in dynamic programming, and these functions here are very complicated. They may involve strange spaces, combinatorial spaces, really very difficult to calculate J star. And that's the reason we have to go to approximations. And the technique is, and the way we generate this optimal controls, this suboptimal control sequence is called approximation in value space. We don't have this jk star. We use some jk tilde, some function that we calculate somehow. And then we do this forward process, but with j star replaced by j tilde. Generate the first control, then generate the corresponding state, and go forward, generating all the controls and states. And I have to do only one minimization at every stage for only one state. For this, and this is convenient. Once you have calculated this J tilde, then it's not so difficult to calculate a suboptimal control sequence by means of this process. So I have told you about a good deal of reinforcement learning for deterministic problems. That's what most of it is. Ways to find out J tilde, ways to do this minimization going forward.
I have a question here.
Yeah, please.
So is the policy means the cost or? You mean previously there's a policy network and you try to find some policy. Is this same as you here? You want to find some J?
Okay. This is deterministic problem, so it's a little easier than stochastic problem. In deterministic problems, okay, if you look at this this expression here, suppose that we do this minimization for every x0. So this will find an optimal control for every possible initial state. Now that would be a policy. It would be a rule that tells you which control to apply for any state that you might be in. Similarly, if instead of calculating doing this minimization for just the state that we end up from a given initial condition, you calculate the minimum for every possible state that you may encounter, that would be a policy. And in the context of approximation, it would be provided by a policy network, perhaps. So we're going to talk about policies and the connection with policy networks once we get into stochastic problems, where this distinction is more important. But the difference between optimal controls and optimal policy is that optimal control sequence is just a sequence of controls, but policies and approximate policies, as provided by policy networks, is a rule for choosing a control at any possible initial state. Like in chess, the state is a policy network has to be able to provide you with move probabilities at any possible chess position. It's not just at a single position, but at any chess position. That's why we call it a policy. Does this answer your question?
Okay, thank you.
Okay, good. So now something that I did not stress here is that this algorithm applies very generally to the dynamic programming algorithm, applies very generally to deterministic problems. The state space can be anything. It can be a finite set, like the set of all schedules for a given scheduling problem. Or it could be an infinite set, like the set of forces that you can apply, propelling forces for a car going forward. Similarly, the states can be either a finite number of them, or they can be an infinite number. Like in chess, there's only a finite number of positions. On the other hand, the state space could be something like the set of all probability distributions over a finite set. Or it could be the set of positions, three-dimensional position velocities of a car, of a vehicle. The beauty of dynamic programming is that it applies to both continuous spaces and discrete spaces, and also for problems that are stationary, where this function fk and the cost gk depends on the stage, but does not depends on the stage, or may not depend on the stage. So the formulation that I gave is as general as it gets for dynamic, for deterministic dynamic programming. On the other hand, finite state problems have a natural appeal in that they are ready to be put into the computer. The computer cannot recognize continuous spaces, can recognize only discrete spaces. And finite state deterministic dynamic programming problems have a connection with shortest path problems, which I'm sure you've heard of at various courses. Okay, suppose that the number of states at every stage is finite. So this is the initial state. We represent it with circles in a graph, nodes of a graph. So this is the initial state, and a state, the x1s, there are 4 of them here, at time 2. X2 can take these values here, and so on. So we can lay out the state space, the state spaces of the problem in a graph, and we can represent controls by these arcs of the graph, where given a state x1 and given a control u1, the arc represents the corresponding transition to the next state. So at this state, there are 2 controls that are available, and they lead from this state to that state, or from this state to that state. So the arcs correspond to state control pairs. So the entire dynamic system of the problem can be laid out graphically on this graph. These are the transitions, and they correspond to various states and controls. And the system equation just tells you what the next node is going to be if you apply control UK, if you took the corresponding branch, and applied control UK at the node XK. Now we can also introduce the costs in this graph. An arc, which is just a state control pair, has a cost associated with it, and we can write this cost along these arcs here. Now, what is the cost of a sequence of controls? Well, a sequence of controls is just a sequence of branches going from the initial state to some artificial, to the terminal state, and an artificial terminal node which the state leads with cost equal to the terminal cost in Gn I gave earlier. So the cost is the sum of the costs along a path that starts from the initial state and ends up at this artificial terminal node. And the problem is equivalent to finding the minimum cost path or shortest path from the initial state to the terminal state. And there are many shortest path algorithms for solving this problem. Dynamic programming is one of them, only one of them. But dynamic programming applies to stochastic problems as well, not only to deterministic problems. These other shortest path problems apply to deterministic problems only.
Professor,
but this, yeah.
So if finding the optimal policy can sort of be reduced to a shortest path problem, what is it about J star that makes it so difficult to calculate, at least in the deterministic sense?
Well, because the number of states can be zillions, okay? Can be more than the number of molecules in the entire universe.
So it's still polynomial in the number of states, but the number of states may just be prohibitively large.
Exactly, yes, it's polynomial in the number of states, but the number of states grows exponentially with the stage, okay? So for example, for a given chess position, the starting chess position, there's a small number of next positions that can occur, okay? I don't know, maybe 30, 40, whatever it is, probably less than that. Now, the states that you can end up after 2 moves is much larger. 3 moves, they go to the cube of the initial, there's a branching factor that is more or less constant within each move. So after 50 moves, the number of possible positions and the number of states in chess is astronomical, let alone going to, okay, so you get the point. Many of the problems that we're going to discuss, and in fact, the problems that will be of interest to us, the combinatorial problems, have an exponentially growing state space with the number of stages, grows exponentially with the number of stages.
I see, okay.
That's the problem. We can't compute J star, we can't store it, okay? On the other hand, we can compute approximations to J star, and that's what the value network does. The value network stores an approximation of J star.
Okay, so is the number of, I guess the number of states would be the number of controls to the power of the number of stages that exist, or that you have in your horizon, right?
For deterministic problems, yes. For
Yes.
stochastic problems, it's even more than that because there's an increase of the branching factor because of the randomness of the next state. But you're right, for deterministic problems, the branching factor is the number of controls at each state.
It seems like you could make kind of a simple recursive algorithm that would calculate the optimal value, provided that you could like store the values of like overlapping or repeated solutions in your dynamic programming framework. But are you saying that?
Well, you're looking at a very special case where there are overlapping solutions. In fact, the states here may be very different than the states here. So there's no overlap. Now, the next example actually will illustrate this.
Okay, I'll wait then.
I'm going to give a couple of examples now to illustrate the dynamic programming algorithm for problems like that. Okay, so here's an example. And I'm going to do this example and then we'll take a break. See how are we doing in terms of time. Ooh, speaking slowly, going slow. But fine, we're doing okay. Let me go to this example here. And this is a very simple scheduling problem. We have 4 operations to schedule, A, B, C, and D. And there's some constraints. You cannot do B unless you do A before that, and you cannot do D unless you do C before that. So a feasible sequence is 4 letters, okay? And there's an issue of modeling this problem. How do we put it into a dynamic programming framework? Well, we do the following. We introduce partial schedules as our states. The initial state is just the empty schedule where we haven't scheduled any operation. Then the first control is the choice of the first operation to schedule. We can start with A or we can start with C. And that will give us a partial schedule consisting of a single operation. Then, so this is the state space at time 1, state space at time 0, state space at time 1. State space at time 2 corresponds to choosing the second operation. And here at A, we can choose either B or we can choose C. We cannot choose D because remember, D must wait until C has been scheduled. So there are two possible transitions. And similarly here, there are another 2 transitions. And then there are more transitions. These states here, this is the states X3, okay? They correspond to the first 3 operations. And then once you schedule the first 3 operations, then the 4th operation is immediate, so we don't have to worry about that. So the transition diagram of states and controls is just the graph that you see here. Now, we introduce costs here for these transitions, and these are the numbers that you see next to the arcs. So having chosen A to choose B, the cost is going to be 2 units. And having chosen AC to choose D rather than B, it costs 6 units, and here it costs 4 units. And these numbers here are the terminal costs, because if we have chosen ABC, then there is also a cost of scheduling D at the end. And in this example, it is 6. Okay. So the circles are the states. The arcs are the controls. The numbers are the costs. Terminal costs, intermediate stages costs. And we want to find a schedule that starts from the initial state and ends up in some terminal node. And that would be, we want to find one that is optimal, has a minimum sum of numbers, okay? So that's our dynamic programming problem. And the dynamic programming idea now is to break down this problem into smaller pieces, tailed subproblems. We're going to start from these general zero-stage subproblems. Then we're going to look at these subproblems that start from here and go to the end. We're going to solve all of them, then go to these subproblems, solve the two of them, and accumulate the optimal costs to go, and then end up going in the beginning. So we start from the last decision and we go backwards. Okay, so here is an illustration. All of this may be trivial for some of you, but I'm going to go quickly through it and you can go over the numbers on your own. Okay, so the terminal cost, the starting function in dynamic programming are these red numbers, okay? And we have one number for every possible terminal state. Now we look at a stage 2 tail subproblem, and this is an example of one. We will look at the stage subproblem that starts at this partial schedule. And we would look at the two possible scheduling decisions, B and D, and then add up the cost of the tail subproblem starting from this next state. So this gives us a 3, 2 plus 1. This gives us a 4, 4 plus, no, I'm sorry, this gives us a 7, 4 plus 3. And we choose the minimum of the two, which corresponds to this arc, and we write the number, this purple number here. That is a single data point written down by the dynamic programming algorithm. Now there are 4 tail subproblems to solve. Here there's only one choice, so 6 plus 3 is 9. Here we compare 4 plus 1 and 6 plus 3, and the 4 plus 1 wins, it's a 5, and so on. So we write down the purple numbers, which is the cost to go for the tail subproblem of length 1 at stage 2. So we record the optimal cost to go, and then we go one step back to the stage 1 tail subproblems. Having obtained the purple numbers, we calculate these orange numbers here. We look at, as an example, we look at this subproblem. And here we compare the two controls, 4 plus 3 and 6 plus 5 is 11. 4 plus 3 wins. We don't have to go all the way to the end. We only have to go to the next state from which we can pick up the purple numbers, which are the optimal cost to go from those states. So we have solved this problem, and we solved this problem also. 5 plus 3, 2 plus 9, this one wins. So now we are ready to go to the initial stage. Having solved the orange problems, we look at the stage 0 subproblem by looking at just the next state here. 5 plus 8 is 13, 3 plus 7 is 10, and this guy is best. So now, note that the stage 0 subproblem is the entire problem, okay? The optimal value at the stage 0 subproblem is the optimal cost, the cost at the initial state, at the empty schedule, and we can contract the optimal sequence going forward. Given these orange numbers, I can do a simple calculation and figure out that this is the first decision, schedule operation C. And now at this state, I can look at these numbers, the purple numbers, and choose the best operation, which is operation A. That moves me to here. And then I can move forward again, look at the red numbers, and look at this operation and that operation. By comparison, I obtain the optimal scheduling decision. And by backwards calculation of optimal cost of tail subproblems and forward generation of the optimal schedule, I have solved my problem. This is the dynamic programming algorithm for this example. Now, okay, there are a few things to note here. This is a trivial problem, okay? Very simple. But suppose you had zillions of states. There would be an incredible amount of calculation involved going backwards. And there would be an incredible amount of storage, computer storage, that you would need to store the states and the numbers, the red numbers and the purple numbers and so on. That's the reason why we have reinforcement learning and we use approximations, because for a larger problem, this algorithm would be totally intractable. Okay, so let's take a break and we'll come back in exactly 10 minutes, okay? It should be 6:05 where you are, so 6:15. Okay, you can see the screen, right?
Yeah, we can see the screen.
Good. So are there any questions from what we've done so far?
So I know I have a question. So we started with saying that some of these algorithms that we're exploring are suboptimal, but the last example you gave us is it seemed like it gives you the optimal solution, right?
Yeah, that's right. Yeah.
And so my question would be does that speed up traditional algorithms? So let's say I'm doing an NP hard problem like a traveling salesman. If I use that sort of algorithm, would that be a better alternative than some of the other ones in the past that have been shown, the other algorithms?
Okay. Actually, we're going to go into a traveling salesman example in the next slide. What happens is that you can solve by dynamic programming within your lifetime, let's say, traveling salesman problems with small dimensions, small size. Once you go into a larger size, then because the problem is NP complete, you can't solve them. You have to resort to approximations. There is no general purpose exact traveling salesman problem algorithm. Okay. Now, we are going to give some pretty good algorithms based on reinforcement learning for traveling salesman problems and also related combinatorial problems. Whether this is going to be better than other methods, it's unclear, but they're competitive and interesting to look at. As far as exact problems are concerned, the reason I gave this previous scheduling example is to demonstrate how hard it is to solve exactly problems of substantial size. So we're not going to be dealing with exact solutions, except for very, very special problems. Generally speaking, in dynamic programming, there are a few favored guys that can be solved. Some problems that admit an easy solution by dynamic programming. But for most problems, and for the problems of interest to us, an exact solution is out of the realm of possibility. So this was just for demonstration of the optimal algorithm. And we're going to be talking about approximations in the future. Does that answer your question?
Yes, it does. Thank you.
Okay, good. Any other question? Okay, so here's another finite state discrete combinatorial example, which is so small that we can solve it with exact dynamic programming. And this is a traveling salesman problem. Traveling salesman problem, you probably have heard of it, involves a number of cities, and you can go from one city to the other at a certain cost. And the traveling salesman problem is to construct a tour whereby you go through every city once and only once. It's a classical combinatorial problem, and we can address by dynamic programming. Generally speaking, we address such combinatorial problems to be addressed by dynamic programming. You have to break them down into pieces. The overall solution has to be broken into small pieces, with each piece being chosen at a stage of the dynamic programming algorithm. So in the context of a traveling this example, we have 4 cities, A, B, C, D, and here is the matrix of inter-city travel costs. First, to go from city A, from city A to city D, there's a cost of 15. To go to city C is a cost of 1, and so on. So this gives you the matrix of costs. And we have to formulate in terms of states and controls. And we will choose an arbitrary city, and we will call it the initial state. And then the other states are going to be partial tours. So let's say this ACB means it's the state that corresponds to going from A to C and then to B, okay? So initial state is A. States at stage 1 are 2 city schedules, 3 city schedules, 4 city schedules, and then we have to pay a terminal cost, which is the cost of going back to the city A, okay? So this is the terminal state. These are the terminal costs, and these are the corresponding costs to go, costs to terminate. They are obtained from this matrix. Now, let's look at the tail subproblems that correspond to these states here. It turns out that these problems are very easy to solve because having chosen 3 cities, then there's the 4th city is determined, and the corresponding costs are what you see. However, we can calculate the costs of the tail subproblems by adding this cost with that cost, 18. Here are 1 and a 3 gives you a 4 and so on. Now, having chosen the first 2 cities, we use these numbers here in order to construct the cost of the tails, in order to construct, to solve the tail subproblems of stage 1. And these involve two decisions, and then we can go one step back to the initial state. So this is just another example of solution by exact dynamic programming. If you had a larger number of cities, the number of states would be exponentially large. And to go back to Jamison's question, there would be no repetitions here, okay? Because the states are all different in this problem. Notice that having gone through the algorithm backwards and generating these red numbers, then we can go forward and generate the optimal policy. In this particular problem, there are two optimal sequences. The one optimal sequence of cities is this one, corresponding to A, B, C, D, and back to A. And it has cost 13, but the same cost is attained by this tour also, the tour A, C, D, B, and then back to A. This can happen, and if you're diligent about it, you can generate the all the optimal solutions by dynamic programming, although when it comes to approximations, this would not be possible. Okay, now motivated by those two previous examples, we can come up with a general method, general formulation for discrete optimization. Now let's go to the most general discrete optimization problem that you can think of, which is to minimize some function g of a variable u, subject to u being in some arbitrarily large but finite set. Now, this problem has no structure at all, but we can introduce structure to it that is amenable to dynamic programming as follows. Okay, u has n components, okay, which we label u0 up to un minus 1. And the order here is, okay, is arbitrary, in fact. But we choose some order, and we introduce an artificial initial state, and we call states at stage 1, the x1s, are the choices for u0. The choices at stage 2 are the pairs, u0 and u1. And each one of those arcs corresponds to having chosen u0, what you choose as u1. And similarly, these are the states that correspond to the partial sequence u0, u1, u2, and so on, all the way to the end. At the end of the final stage, we get complete solutions, which have a corresponding cost. And the cost here is just the terminal cost. So just as we had partial tours for the traveling salesman problem, here we have partial solutions for an arbitrary discrete optimization problem. So these bullets here describe what I just said. These are the states. The controls are the components of the solution. The terminal cost is g of u, and so on. Okay, now coming back to an earlier comment, does it make sense to use exact dynamic programming to solve this problem? Well, the answer is no. It's not a good idea because the state space grows exponentially with the number of components. And it can get astronomical very quickly. On the other hand, we are going to provide approximate dynamic programming methods, like the rollout I mentioned earlier in connection with AlphaZero, which do not need to consider the entire space, which can be very large. Just navigate through using approximations and construct a solution which is suboptimal. So this kind of formulation is silly if you're considering an exact solution method, but it's quite relevant and makes sense if you're considering approximation methods based on reinforcement learning and approximate dynamic programming ideas. We're going to come back to this formulation when we talk about combinatorial problems, discrete optimization problems, although this will take us some time to get there, probably another three lectures or so. Okay. So now we talked about finite state deterministic problems. It's possible to consider stochastic problems, where the next state is affected by a random parameter in addition to xk and uk. We talked about we can extend to infinite horizon problems, where there's an infinite number of stages. And there are mathematical complications in doing this because the mathematics of infinity, basically, you're accumulating costs over an infinite number of stages. The theory is quite deep. We're going to get partly into that theory, partly rigorously, partly through intuition, towards the end of the class. Okay. In a lot of our formulation, we're going to use policies that have complete information, complete state information. Like in chess, the chess player or the chess program has exact knowledge of the state. The the chess position, knows that state perfectly. On the other hand, there are many problems where the state is not known perfectly. Like, for example, a vehicle, you may know its position exactly, but you may not know its velocity. Or you may know its position with some error of the radar, let's say, that tracks the position. These problems are called partial state information problems, or POMDP, if you have heard of them. And they're much more difficult than perfect state information problems. However, from the conceptual theoretical point of view, they are no different. You can compare them to problems of perfect state information and then apply dynamic programming to these problems. And we are going to discuss how this conversion is done in the next lecture, probably. And we're going to use it later as we discuss various examples. Okay, dynamic programming can be applied in the context of minimax problems, our worst case design type of problems, where there is uncertainty and we want to guard against the worst case of that uncertainty. Similarly, there is a dynamic programming algorithm for game problems, two-person game problems. And this is the algorithm that is used in AlphaZero. AlphaZero involves two players, so it's a little different than the one-player problems that we have discussed so far. The dynamic programming theory is more complex, and we're not going to go into minimax or game problems very much in this course, except in the way of orientation and also motivation using the backgammon and the chess programs that have been developed. Okay, so that marks the end of this, of the technical content of this lecture. Let me say a few things about how this course is organized. And please speak up and bring up your questions.
I actually had a question.
Yes,
could you
please.
go back to, it's a bit earlier. Could you go back to slide 19?
19. Okay.
So for the
Is that it?
optimal cost function, if the last bullet point, if x of 0 is replaced by a state history, does that also, the equation still holds the principle of optimality?
Okay, I'm not sure I understood your question.
Uh,
Are you talking about a deterministic problem or a problem that involves some stochastic parameters?
Just a deterministic problem, but it is not a first order Markovian process. It's a higher order. Can the same exact DP method you described be used?
Okay. For deterministic problems, I'm not quite sure what you mean by a Markov process. Do you mean
Or
that
for
the
a
state-
non-deterministic, I mean for a stochastic problem, but it's higher order in Markov.
higher order in the sense that the state depends on several previous states, right?
That is correct.
Okay. It is covered by the theory that we're going to develop.
Okay.
Any problem, okay, here's something that, here's a big statement. Any optimization problem that you can think of, there's a way to formulate it in terms of dynamic programming. It doesn't matter if there are delays in the effect of controls. Doesn't matter if the state depends on several previous states. Doesn't matter if it's deterministic, stochastic. Doesn't matter if there's always a way to reformulate a problem so that it fits our framework. The way you would do it when you have this Markovianity that you mentioned, where you have dependence to several previous states, is by lumping all the states that appear in this equation into one. Construct a bigger state, what's called state augmentation. If you look at section 1.3 of your notes, you'll see a subsection called state augmentation. which deals with that sort of thing. So you may want to read that, but yeah, the short answer to your question is yes. Any problem that involves multiple dependencies is just a matter of redefinition of the state. The state is a mathematical object in our context, and we can choose anything we want for state.
I see. Thank you.
Okay, good. Any other questions? Okay. So my objective is to get you interested in reinforcement learning and try to connect it with your own research interests, wherever they come from. I know you come from several different disciplines, electrical, mechanical, computer science, operational research, industrial engineering. There are points of contact of reinforcement learning with whatever your discipline is. Of course, it has to involve dynamic systems and so on, and optimization. But we are going to cover a very broad range of methodologies with very broad range of applications, and I hope that you will find a match with what you're interested in. And aside from homework, we're going to have a research-oriented term paper. That's going to be the big part of your grade, your assignment. And you will have a choice of two things: a mini research project that relates to the content of the course of your choice. Choose anything that you want that is of interest to you. If you have already worked on this topic and you have done a thesis, master's thesis, or whatever, or PhD thesis, it's fine to work on it for this term paper. Moreover, you may work in teams of up to 3 persons. And ideally, I'd like to encourage you to try that. Unfortunately, we have limited time of 1 semester, and very often that's not enough to get started in research. So if you can do it, fine. If you cannot do it, then you can do a read and report type of term paper, whereby you read some literature and you write a term paper of the order of 15 pages or so. Now, I'm going to be available to interact with you on your research ideas. And at the end, I'm going to select some class presentations for the last lecture or the 2 lectures, depending on how many we have. In the past 2 offerings of this course, I think that about 30% or 40% of the students were involved in mini research projects. So the majority was term papers. That's a reflection of the fact that it's not very easy to do this research type of project. But I want to encourage you to try, and hopefully many of you will manage to do good work in projects. And for me, that would be very satisfying to see a few term projects, 5, 10 resulting from this course. Okay, a sensitive subject. Is this a question?
Yeah. So how many pages you mentioned for the term paper? 15 or 50 pages is required for the term paper. You said about 15 pages or 50 pages?
15 pages.
Okay. Thank you.
And this is flexible, okay, obviously. 15 papers, not including any code and so on. 15 pages. Basically, the number of pages is not so important, but rather what's important is to be able to make interconnections between the research. But obviously, these 2, 3 have to be related. They have to be a coherent whole. And big part of your effort should be directed towards making the connections between those and making an assessment of these of the research that's presented in these papers.
Thank you.
Okay. Okay, a sensitive subject. Unfortunately, you come from all walks of life, all walks of engineering, and I welcome that. On the other hand, you may be used to a different notation. You may come from reinforcement learning. You're used to the terminology and notation that's used in artificial intelligence. As I explained earlier, the notation used there is transition probability notation, whereas we use a system equation notation, at least for continuous state problems and deterministic problems. I want to strongly encourage you to use the notation and terminology of this course. I think you'll find the notes that are very precise in terms of the use of notation, and I want you to make a special effort to get accustomed to the notation of the course. It's not that I am sort of self-centered and I want you to adopt my way of viewing things, but for me to be able to read your work, if it's written in different notations, chances are that I will not be able to. So please try to use the notation of the course. And in addition to getting more help from me, it's a good exercise, just the translation of one system of notation that you're used to into the notation of this course will be a good exercise for you to go through. Okay, so I have this course deals with approximations. It's an approximate syllabus. We are going to spend 3 lectures, including this one, into the connections between exact and approximate dynamic programming, and also examples of problem formulation, like I gave today for discrete deterministic problems. Then we're going to go into approximation in value space, rollout, and rollout. This has to do, this is like the online play type of algorithm that is used in AlphaZero. We are going to give several different versions of that, deterministic problems, stochastic problems, and so on, various contexts, including multi-agent systems, model predictive control, and combinatorial optimization. So this will take us to lecture 9, which is quite a bit of time for going forward. And then we're going to talk about parametric approximation architectures, value and policy networks, including neural networks and their training methods. And we're going to connect this material with the preceding material. All of this up to lecture 10 is going to be, for the most part, finite horizon problems. However, we will see that a lot of the algorithmic concepts that we're going to develop for finite horizon problems also apply to infinite horizon problems. Still, we're going to spend some time looking at them in some detail and somewhat more rigorously. Excuse me. A major algorithm is policy iteration. This is the offline training type of algorithm for AlphaZero that I discussed, and various variants of that. The use of policy iteration connection with value and policy networks. Then I'm going to talk about distributed algorithms that are well suited for parallelization, partitioning the state space in pieces and executing dynamic programming type of algorithms over the different pieces. And then project presentations is the last lecture, and it may also need a little bit more if the number of presentations does not fit into 2.5 hours. The mathematical requirements for this course. I'll have to confess that I'm a mathematician, and I like mathematics. I spent most of my life doing mathematics. However, I have found that reinforcement learning ideas involve a fair amount of intuition where mathematics alone are not going to carry you through. You need some understanding, you need some creativity, some inventiveness, and some intuition into the problem, into the methods, and also intuitions of the problems at hand. So we're not going to emphasize mathematics in this course, except that we're going to try to be rigorous in our use of common language, of natural language, okay? We're going to be making precise statements, even if they do not involve mathematics. Our main objective is to use the mathematics to the extent needed to develop insight, and that's our objective. However, to develop insight, we need some kind of a structured thought, a framework for structured thought. And mathematical reasoning is the most suitable for doing this. And as opposed to software, okay? A lot of you are doing software. I love software, but I think you'll be better served in thinking through the topics of this class through mathematics rather than through computer software. I have a quotation here from a New York Times article by a Cornell professor, Storgatz, I think it's his name. And it's musings about machine learning. The problem with machine learning is that the algorithms are so complicated, and neural networks in particular are so complicated that you can't understand what's going on. We don't know why they work when they work, so we don't know if they can be trusted from one application to another. It's very important to have insight, and there's going to be a tension between algorithms and complicated computer algorithms and insight as we go forward. And that's something to think about. And with an eye towards motivation of developing insight. We do need insight, and we're going to try to develop this to the extent possible for the methodology that we are going to talk about. Okay, the next lecture. We will cover stochastic dynamic programming, a generalization of the deterministic dynamic programming. We're going to talk about Q factors and how dynamic programming algorithms can be written in terms of Q factors. And we'll say what that means. Approximation in value space, and examples of discrete and continuous dynamic programming problems. I recommend strongly that you read as much of the class notes as you can. And also, there are video lectures from the 2019 offering of the class at my website, as well as slides from these video lectures. Perhaps you can watch some of those before you come to class. I think that will be helpful because we're going to be going fairly fast, covering a lot of material. So that's the end of the lecture. Do you have any questions?
I have a question about the coding part of this course. So is the reinforcement learning like supervised learning? We can use some open source packages such as TensorFlow, or we need to develop the packages based on Python or something?
I think that you will not have opportunity to use available software except for neural network training. There are software for neural network training, and you can use those to train neural networks. On the other hand, Beyond that, it's unlikely that you'll be able to get very far with existing software. To begin with, they're very unreliable. And also, what I'm looking for is more than just an application of existing software, using the codes. I'm looking more towards learning through developing algorithms that are specific to the application domain you're interested in. However, for training neural networks, I think not only it's permissible, but it's also essential that you use existing software, because it's extremely difficult to develop your own software for training neural networks.
Okay, thank you.
Okay. Any other questions?
Professor, you mentioned the class was pass-fail, so will we not receive letter grades, or how does that work?
I'm not sure. I'm not sure because I'm not quite sure about the ASU requirements. But I think, why is it important that you receive a grade, a letter grade?
Oh, I don't know that it's necessarily important. I was just curious to how it works, like, or what you had in mind.
Maybe I'll give grades. I can tell you ahead of time. Everybody who stays with the course deserves an A. Everybody who does not deserve an A will have dropped out. Well, so it's an easy answer to this, and I'll check and find out.
Okay, thank you.
Okay. Any other questions? You know my email address. If you have any questions, you can address them to me, and I'll be happy to try to resolve them. So, see you all next week.
Thank you.
Thank you, Professor.